So I'm starting recording now. Makita siya. So, kinetics of corrosion prepared by yours truly. Yes, yours truly. So, sa kinetics of corrosion, what we're finding out is how fast your corrosion occurs. So, kaya ko ginamit na si meter kasi speed. Lightning McQueen speed. And nag-corrode din siya. Topical. Yes. Tawag dyan is whimsy. So, yun lang, kinetics of corrosion, how fast? So, we have different ways to express the corrosion rate. You have corrosion penetration rate. So, corrosion penetration rate, this is just the penetration rate of corrosion. And ang units nito, wait, nasan yung aking setup. So, ang corrosion penetration rate natin, this is just thickness per time. So thickness loss of material per unit of time, and CPR is equal to KW over rho AT, where K, hopefully this works, where K is, yes, yon, where K here, this is just a constant. In actuality, ang totoong formula ni CPR is wala tong K. But yung K natin, this is just a conversion constant para yung mga engineers natin na ayaw mag-compute, meron lang silang inputs, meron ka lang conversion factor na ginagamit. So, for example, as we weight, density, surface area, and time. So for example, yung problem ni Callister, 17.12, is thick steel sheet of area of 400 cm squared is exposed to air near the ocean after a 1-year period. It was found to experience a weight loss of 375 grams due to corrosion. To what rate of corrosion in mils per year does this correspond? So the density of steel is assumed to be 7.89 grams per cm cubed, which is around the density of iron. So to get CPR, we use our formula. We have KW over rho 80. Wow, gumagalaw siya. I'm so proud of this. Then, plugging in the inputs, K is 532. Weight is 375 grams, but in the formula, we need to make it milligrams. So times 10 to the 3 milligrams over density, over surface area. But since we're looking for mils per year, so note, ang mils natin, mil is just equal to 1/1000 of an inch. So we convert that, we get this, and makita natin it's 46.7 mils per year. An alternate way of solving this problem without using the conversion constant is just solving it directly. So we look for thickness over time. So we use CPR is equal to W over rho 80, wala na yung K. But this time, dapat cognizant na tayo dun sa constants natin since magko-convert na tayo. So 375 grams over 78.9 grams per cm cubed over times 400 cm squared times 1 year. So we need to have our constants be pare-pareho. So we have 0.118 cm per year. So we just convert cm to mils. Ang cm natin, again, is 1 mil is equal to 0.00254 cm. And makita natin yung same answer. Wow, same answer. Yes. So yun, madali lang naman siya. But usually, hindi naman challenge sa inyo to. So next, we have the corrosion rate as a function of current density. So R is equal to I over NF, where I is the current density, N is the number of electrons exchanged in the reaction, and F is Faraday's constant, which is equal to 96,500 coulombs per mole. So from here, ang current density natin, this has a units of coulombs per meter squared second. Number of electron exchange, this is just from the reaction, wala yung units, and yung Faraday's constant natin, this is coulombs per mole. So good morning, Fabs. Hi. Thanks for joining us today. So, canceling, units, then at the units niya, makuha natin yung corrosion rate mo will have units of moles per meter squared second. We always have the option of making this in terms of mass. We just multiply this by density or something, or CPR or something. So mula dito, maka-convert na rin naman natin siya into our other corrosion rates. So reminder lang uli, anytime na may tanong kayo, feel free to interrupt me during this discussion because frankly, nakakapagod na magsalita ng siguro mga 1 oras straight. Water. Oh my God, mas sabog ako sa online kaysa sa normal na classes. Next, we have the electrical double layer. So electrical double layer shows us how the metal surface and the electrolyte interacts. This basically provides us an idea on how the mechanism of corrosion occurs. Ang important lang dito is from the electrical double layers, meron tayong Stern, Goy-Chapman, and si Helmholtz yata. I forgot. Well, basta alam niyan. Ginawa niya yung activity 2.4. The thing with the electrical double layer is just it tells us how the electrolyte and your metal surface interacts, and mula dito makita natin kung yung control ba niya is reaction control or diffusion or mass transfer control. So yung pagpasok ba ni ions sa interface or yung reaction mismo sa interface, yung control. So mula dun sa electrical double layers natin, makuha lang natin in different polarization models natin, which will be the meat of the discussion today. Meat, yes. I'm hungry, oh my God. So now, I call this meeting just for the discussion of polarization. So polarization is probably the hardest concept to grasp in MatE 171. Otherwise, MatE 171 is a very, very easy subject. And also polarization and the knowledge of polarization curves is one of the four important diagrams that the materials engineer must know. So if you're curious kung ano yung 3 na other diagrams important sa mga materials engineer, hopefully natandaan ko siya. So first, ang pinaka-important sa atin is yung, oh my God, nakalimutan ko iba. Phase diagram. Yung second is Fourier diagram. Yung pangatlo is yung polarization curves natin. And yung fourth is yung band diagrams natin. So yun yung 4 gods of the materials engineering na diagrams. Ito yung kailangan yung malaman para maging competitive naman kayo once pinalabas na namin kayo from the MatE. So basahin yung 4 na diagrams na yun. Ano yun, Rick?
Ano yung last? Yung
band diagram.
Yung sa AAA?
Yung sa MatE 121.
About that.
Yun yung basta from the band diagram, kailangan nyo makuha yung band gap, yung kung conductor ba siya, insulator, mga ganyan. Though mas marami pa siyang knowledge. Though yun, important siya. Sana. Important talaga siya. Kasi most of the material properties, electrical, thermal, makuha natin from, electrical properties, electronic, makuha natin from the band diagram. So anyways, aside, polarization, we discussed this to know paano ba, kung gaano kabilis nagko-corrode ang ating system. Since corrosion is an electrochemical reaction, there is a current associated with the said reaction. And due to this current, wala tayo sa equilibrium. Since may gumagalaw na tayong charges, we are not in an electrical or a chemical equilibrium anymore. Then, since we are not in equilibrium, magbabago na yung equilibrium potentials natin, yung ating potential difference. So consider a copper ion. This is not Daniel cell. Forgive the change. Let's change this one. This is not Daniel cell. Consider a copper Fe cell. Oh my God. Shift F5. Consider a copper iron cell. The potential difference of copper and zinc without current flow is around 1 volt. I think mga ganun. Around 1 volt or 0.8, 0.9. So, this is yung nasa kanan. Ito. Yung nasa kanan, this is a polarization setup. So, this is just a lab equipment to know kung ano yung polarization curves natin for a given electrochemical reaction. So, we have iron and copper here. And dito meron tayong variable resistor. So a variable resistor just varies our resistance from very high to very low. At very high resistance, it is as if meron tayo ng open na circuit. So pag open yung circuit mo, it is as if na wala kang connection between iron and copper. So the potential difference in here between iron and copper will be yung equilibrium potential difference between the two. So yun yung malaking potential difference, yung nakita natin sa battery as kunyari 1.5 volts. But so dito, your iron is the anode and your copper is your cathode because copper has a higher reduction potential, a more positive reduction potential than your iron. So in this case, we will see that iron will be the one corroded while copper will be yung ating cathode, which will not be as corroded as much. As we decrease the resistance of the variable resistor, we're approaching a condition in which nagiging short circuit na siya. So pag short circuit na siya, yung resistance within the circuit or in the diagram becomes zero because we decrease the resistance, ang flow na lang, nagiging flow na lang siya ng electrons. We see that the potential of the anode and the cathode, so potential of the anode and the cathode as the current increases tends toward a more central value. And our system will stop shifting in potential when they have the same value na as each other. So during corrosion, the potentials in the electrons will begin shifting until they have about the same potential. So in this diagram, it is here. Copper shifted downwards, iron shifted upwards to our corrosion potential here. And yung intersection nito, itong dalawa, so we have V versus log current. So the intersection of these two, this tells us the corrosion potential and more importantly for us, the the corrosion current or the current associated with corrosion. So kanina nakita natin from our previous formula that the current associated with corrosion can be directly translated into, let's say, the material loss. Since redox reactions natin, it involves current. So pag mas mataas yung current, ina-expect natin mas mabilis yung corrosion natin. So sa polarization, the phenomena of polarization in your electrochemical reactions such as in corrosion, this is the shift of your potential from its equilibrium value down to its stable value in corrosion. So, yeah. So we have two different types of corrosion. Oh, wait. Yeah. So two different types of polarization, in terms of paano yung shift niya. You have your anodic and your cathodic polarization. So anodic polarization natin, nag-shift siya to a positive direction. So when meron kang anode, ina-expect natin if it is anodic in that electrochemical reaction, so pag anodic siya, it's oxidized, it will shift to a more positive direction. Tataas yung potential niya from its equilibrium value. And sa anodic polarization, if your material or if your metal experiences anodic polarization, essentially always na tumataas yung corrosion rate niya. Sa cathodic polarization naman, nag-shift tayo down to a negative direction, yung potential natin, and yun, makita natin baba siya. So yung anodic and cathodic polarization natin na distinctions, this just pertains to kung paano yung shift ng potential natin when there is now a current. So basically, anode and cathode lang yan. Then. And to quantify the shift, the polarization in, let's say, the potential, we have what we call your overvoltage. Yung overvoltage natin, this just describes the magnitude of the displacement in polarization. And it is symbolized by N. Ano to? Eta. Oh my God, wala na akong battery. By eta. So yung eta natin is equal to the measured potential E at our specified current minus yung equilibrium potential natin. This is yung equilibrium reduction or reduction potential natin or oxidation potential. Equilibrium reduction potential versus a standard reference electrode. So basically, yung over voltage natin, this is just ito. It's just your over voltage. So for your cathodic polarization, the over voltage is V core minus VCU. For this one, this is VFE minus V core minus VFE. So yan. So that is your over voltage. So now let's go into the different types of polarization. So we basically consider two different types of polarization depending on whether on reaction control siya, reaction control, or if it is diffusion control. So first, we have your activation polarization. Ang activation polarization natin, basically, ang control niyan is dun sa reaction interface na natin. So electrochemical reactions consist of a sequence of steps that occur in series at the interface between the electrode and electrolyte solutions. So this is a flashback to your MatE 103. So at the reaction interface, there are multiple reaction steps that your reaction may undergo to completion. Kasi meron tayong different activation energies for each of these reaction steps. And activation polarization refers when your polarization or when your condition is controlled by the slowest step in our reaction. The slowest step in the series. So take for example, the reduction of hydrogen ion on zinc electrode. The reduction of hydrogen ion to H2 on the zinc surface is H plus to H plus 2 electron minus to form H2 gas. This happens in our zinc solid surface. So yung reduction reaction mo happens at the zinc surface. So they found that there are 4 steps necessary for this reaction. One is the adsorption of hydrogen onto the zinc surface. So how do I clear the screen? So clear ink. So yung first step natin, it's this one. Adsorption of hydrogen ions onto the zinc surface. Second is yung pag-capture ni hydrogen ion ng isang electron from the zinc to form hydrogen atom. Third step is the combination of your 2 hydrogen atoms to form hydrogen gas. And yung fourth is yung release of your H2 and the combination of your different H2 molecules to form a bubble. So they found that in the reduction of hydrogen plus on the zinc electrode, the rate determining step is the second and third steps. Yung capture of the hydrogen ion of an electron and yung combination of your hydrogen atoms to form your hydrogen molecule. So in this case, since yung ating process is controlled by, let's say, this reaction or reaction controlled siya, makita natin that it will be activation polarization na yung mag-govern sa ating polarization reaction for our system. So for our purposes, yung polarization natin, for now, we can just think of it as yung voltage versus current change that is necessary to find yung corrosion rate natin. So basically, yun ang may application natin sa corrosion. And for activation polarization, the polarization curve is governed by what we call the Tafel equation. The Tafel equation is just a linear curve in the log scale. So your over potential here, your activation polarization, is equal to the Tafel slope plus or minus the Tafel slope beta multiplied by log of I, where I is your current density, over I naught, where I naught is your exchange current density. So the Tafel slope is positive or negative depending on whether anodic or cathodic yung polarization natin. Pag anodic yung polarization mo, the Tafel slope is positive. Beta is positive if anodic. Meanwhile, beta is negative if it is cathodic. Kasi makita lang natin from this equation, ganito yung Tafel plot. No? Log I and over potential N or E. So what is now your exchange current density? So the exchange current density is basically kung gaano kabilis ang reduction and oxidation reactions mo at equilibrium. So the rate of oxidation and reduction reaches an equilibrium, at an equilibrium is equal, and therefore wala tayong no net current. So the exchange current density is a misnomer since there is really no net current on the surface of our electrode. It is merely a convenient way of showing the rates of oxidation and reduction at equilibrium. So basically, it is just parang yung baseline natin at yung pinakamababang current ng reduction in oxidation potential mo. And for our purposes, it's just simpler to take this as a constant. Parang it's a constant or a necessary variable to solve yung ating polarization curves. And the exchange current density, this is affected by the nature of the reaction, concentration of the reactants, electrode material, temperature, and the surface roughness. So all of these factors also affect yung ating corrosion rate. So parang yan yung pinanggalingan or yung baseline or yung basis ng ating corrosion. Diyan siya nagsimula. So now, this. So this is a sample na plot of your activation polarization. So makita natin for activation polarization, we have E or over potential in the y-axis. Meanwhile, in the x-axis, we have log of I or log of capital I. So it may be log of current density or log of current itself. Yung difference lang nila is yung isa may area, yung isa wala. So for activation polarization, you have this plot. So beta is the slope. Positive beta, negative beta, this is their Tafel slope. I is your current density at a given over potential. And I naught is your exchange current density. So again, pag anodic yung polarization natin, remove our erase all ink. If anodic yung polarization natin, this is an anode reaction. This is anodic. Anode. And yung reduction, yung reduction natin, so nag-capture siya ng electron, this is your cathode reaction. Negative and positive beta for each of these. Cathode is negative beta, anode is positive beta, just corresponding to the same flow or same sense nung nakita natin kanina. May tanong ba kayo? Well, I'm
Yung tanong po.
Go.
Hindi ko alam kung na-discuss umiyaw sandali.
Go lang.
So hindi po ganyan yung graph na both anode at cathode magpapakita at the same time?
Anong hindi ganito yung graph?
Like, for example, kasi di ba bibigyan ka ng equation na eta equals plus beta. So yung makikita mo lang sa graph, yung anode lang.
Yes.
So hindi ganyan dapat na dalawa.
Actually, mas tama na itong dalawa yung lagay natin. But kasi makita natin later na pag sa redox reaction, sa polarization curves natin, meron tayong polarization ng isang component nung anode natin, polarization nung isa pang half reaction natin, tapos tinitingnan lang natin yung intersection nilang dalawa para makuha yung ating corrosion. So, mai-ignore yung isang branch. Pero pag complete yung discussion natin, usually nalagay natin yung pareho. Kasi tinitingnan lang naman natin kung saan sila mag-intersect later for two different, let's say, metals. Or two different
Sir,
reactions. Go.
sir, question po.
Go.
For the beta, is it the same? Will the slope be the same for the anode and the cathode?
Usually, yes. So, buti yung pinaalala mo sa akin to, Meg. So, beta, your beta is actually a function of the number of electrons exchanged during the reaction. So, usually, your anode and cathode na beta, this will be the same. Different lang sila ng signs. And yung values ng beta natin is from 0.05 to 0.15 volts usually. So pag 0.05 volts is around siguro parang isang electron in exchange, and 0.15 parang tatlong electrons in exchange in the half reaction. So for hydrogen, yung beta nito, this is around 0.10. Tama, 0.10. 0.1. Yan. 0.1. So thank you. So shout out kay Meg and Rick for asking questions.
Sir,
Go Seth.
nag-iiba ba yung beta? It depende sa redox reaction or set na siya for hydrogen na ganun talaga yung
Set na siya for the half reactions. So for hydrogen, lagi siyang 0.10. For let's say, for zinc, tama ba? For ibang set na siya, may set values na siya usually. Depende din sa half reaction and din sa environment na kung nasan siya. But kung nag-couple kayo ng iba't ibang materials, hindi dapat sila mag-interact. So constant na kasi yung beta natin. The Tafel slope is we can take it as a material constant or a system constant.
So sir, kung like for example, ang kinopol na metals ay yung isa 1 electron lang, tapos yung isa 2 electrons. Yung 1 electron lang, 'di ba, ita times 2 mo yung reaction para mag-equilibrium sila nung other reaction.
Yes.
So ita times 2 din ba yung slope nun?
No.
Okay.
So diretso na siya. Beta will be 0.05. So kung ano yung binigay na beta sa inyo sa, let's say, sa given for that material, yun ang gagamitin nyo. Huwag na kayong maghanap ng iba. So wala na tayo, hindi na natin minamanipulate yung beta. We just take it as is. So thank you. Thank you, Sid. Thank you, Dave. And thank you for Mother for giving me more water. So that is for activation polarization. Ang layo ng mic. Next, we have concentration polarization. Concentration polarization now exists when the reaction rate is limited by diffusion in the solution. So it happens either at high reduction rates or low concentration of ions, which forms a depletion zone. High reduction reaction rates or low concentration of ions, which forms a depletion zone. So basically, sa concentration polarization, ang nangyayari, sobrang bilis ng reaction natin that instead of reaction control na yung ating interface, nagiging mass transfer control na siya. So ito yung MTBL natin when you remember your MatE 103 sa kinetics. So rather than reaction control, mass transfer control na siya. And yung depletion zone natin, ito yung parang mass transfer boundary layer. Tama ba? MTBL. Or, yeah. Ooh, it moves. Wow. So, let's just highlight the difference between activation and concentration polarization. Sa activation polarization, makita natin that there is no depletion zone since yung diffusion natin, the rate of diffusion is faster than the rate of your reaction. Since reaction control tayo dito, this is reaction control. On the other hand, sa concentration polarization, this happens when the rate of reaction is very fast in such that yung ating diffusion cannot keep up. So dito nagkakaroon tayong diffusion control. So kasi pagpasok ni hydrogen ion dito, let's say, react na agad siya and H2 agad siya. So hindi nabibigyan ng enough time yung H plus na makapasok and nagiging rate determining step natin, RDS na natin si diffusion. If that makes sense. So concentration polarization again happens when the reaction rate is too fast or your diffusion is very slow. Kasi gusto natin maging control yung diffusion mo. And for concentration polarization, it is governed by this equation. 2.3 RT over NF, where R is your gas constant, 8.314, or the Boltzmann constant, joules per mole Kelvin. T is the temperature of your medium. N is the number of electrons exchanged in the reaction. And F is your Faraday's constant, multiplied by log times 1 minus I over IL, where IL is the limiting diffusion current density, which is equal to dN FCB over X, where dN is the diffusion coefficient, CB is the concentration of the ions in the bulk solution, and X is the thickness of the diffusion layer. So yan yung equation natin. So usually makakuha naman natin yung dN and CB, so we can get IL. Yung X natin, also we can get IL, so to get the thickness of the diffusion layer. Yung IL natin, this is basically, yan yung parang maximum na current or limiting current. Ito yung maximum na current na pwede nating makuha sa concentration polarization. And pag graph natin to, it would look something like this. So this is NC over potential. Yung IL natin, this is just your limiting current. Sinasabi lang sa concentration polarization natin that your potential, that your current will not be greater than your IL. And sa shape ng concentration polarization natin, meron tayong abrupt change. Boom. So if I is equal to 0, then your concentration over voltage is absent. I equals 0, wala tayong over voltage. As I approaches IL, nakita natin that your concentration over voltage is very, very large. What is that? Sure. And for our purposes, again, ang important lang sa atin siguro for the corrosion rates or for the kinetics is that we know na ganito yung shape niya. Ito yung formula nito. Ito yung formula niya para later, pag nag-compute na tayo, makuha na natin yung corrosion, yung corrosion potential, and yung corrosion current natin. So, kung mapapansin nyo, sa concentration polarization, pababa lang siya. So, pag pababa lang siya, this is only a cathodic polarization. Bakit sa concentration polarization, wala tayong anodic na reaction? Anodic polarization is not considered. Or better yet, siguro ang tanong mas maganda, bakit sa anodic polarization, hindi siya magiging controlled by concentration polarization? So tingin nyo bakit? May mag-a-attempt ba? Bakit wala? Ang hirap, no? Kasi hindi ko alam eh. Pagay na kaya naman ba? Sige. Sa tingin nyo, bakit? Sige, magtawag tayo. Meg, as representative. And then si Cedric na lang.
Sure.
Kasi si Meg, nag-respond na si Meg.
Si Sed na si Sed.
Bad move.
Bakit? Ikaw ang top ng batch nyo.
Yes.
So, hindi na-feel.
Ay, di pala ako, sir.
Ha? Sige, si Rick na lang. Sige.
Correct. Sir.
Meg, sa tingin mo, bakit walang concentration polarization control sa anodic reactions?
Sir, I'm really not sure. Baka kasi sa anode nangyayari talaga yung corrosion sa mas stable sa cathode. Maybe.
Bakit ganun?
I don't know.
Sige, tawagin natin Cedric. Cedric, ikaw.
Sir, hindi ko rin actually.
Bakit? Bakit sa tingin nyo? Wala ba nakakaalam? Huwag kayo mag-alala, pero hindi ko rin alam to eh. Na-realize ko lang siya kahapon.
Sir, baka kasi hindi
Meg.
hirap i-measure yung current sa pag nagko-corrode na siya.
Not really.
No ba?
No.
Okay.
It has something to do with the mechanism of the reactions. So, recall natin yung ating clue. So, ang ating reduction is, ano reduction natin? H plus, let's say, M plus E minus 2M. Oxidation mo is the reverse. M to M plus E minus. So mula dito, dapat magkakaroon tayo ng clue kung bakit ito, pwede siyang concentration control, concentration or diffusion control, and ito, not diffusion control. So tingin nyo mula dito, bakit yung pangalawa or yung ating oxidation, bakit ito, hindi ito magiging diffusion control?
Kasi mas stable yung solid state ng metal.
Not really.
Kasi may ions, sir. Ions yung reactants mo sa cathode.
So,
Ions yung nagde-diffuse, sir. E pag metal ka, ay pag dun sa cathode, solid ka lang.
okay. Tapos? So, ano meron kung ions ka lang, Mon? Malapit ka na, Mon.
Random lang kaya ko, sir.
Unstable ba?
Nakikerry
Partly,
ka ng...
Malapit na si Mon. So, meron kasing ions, but kailangan rin nating tignan yung kapartner ni ions. Ay,
Yung electrolyte?
anong electrolyte?
Tapos yung electrons yung
Electron.
gumagalaw.
So, kasi, tama, malapit na si Mon. So, kompleto ko na siya. So, sa reaction, meron kasi tayong dalawa na nagre-react. You need your ion and your electron to react. And para mag-react sila, dapat mag-meet sila sa interface. So, nagdi-diffuse dapat si hydrogen to your metal to get your electron from the metal. Tama, di ba? So, meron kang diffusion step. In contrast, dito sa anode reaction mo or sa metal, yung metal mo, hindi na yung magdi-diffuse. Kasi nandyan na siya. Ang gagawin niya na lang, magpapakawalan lang siyang electron. No need for diffusion. And hindi siya magiging diffusion controlled since there are no diffusion events going into the metal anymore. So, labas lang siya na labas. Gets ba? Sana. So, parang ganun lang siya. Pag nakita niyo yung yung reaction, kaya sa concentration polarization, lagi siyang reduction, reaction na yung kino-consider natin. Kasi dun lang naman yung nagkakaroon ng capture ng electron. Sa oxidation, labas lang siya. Wala kang diffusion, so hindi ka makakontrol ni concentration. Yan. And lastly, we can combine. So usually, hindi lang naman activation or concentration polarization ang nangyayari sa isang electrode. I mean, for a reduction electrode. Both activation and concentration polarization usually occur at an electrode. So the activation polarization dominates at low reaction rates since reaction control siya. And concentration polarization naman prevails at the high reaction rate since mas mabagal na yung diffusion mo than yung reaction. And to get the combined polarization, we just add yung two polarization curves natin. Eta of T is equal to eta of E plus eta of C. Shh! Quiet! Ngay. So, mula dito, we just add yung ating two overpotential reactions, yung dalawang log, yung may Tafel slope, and yung merong I minus I, 1 minus I over IL to get yung combined polarization natin. So now we have the knowledge of these different polarization reactions. We can now go into our mixed potential theory. So mixed potential theory, the theory states that any electrochemical reaction can be divided into two or more partial oxidation and reduction reactions, and there can be no net accumulation of electric charge during an electrochemical reaction. Ang consequence lang ng mixed potential theory is that during the corrosion of an electrically isolated metal sample, the total rate of oxidation should be equal to the total rate of reduction for the system. Again, the total rate of oxidation is equal to the total rate of reduction. So example problem from problem 18.2 from our favorite textbook, Callister. So zinc experienced corrosion in an acidic solution according to the reaction. According to the reaction, zinc to zinc 2 plus 2 electron minus, and you have acidic condition. So you have H2 to form, H plus 2 plus 2 electron minus to form H2 gas. The rates of both oxidation and reduction half reactions are controlled by activation polarization. So if activation polarization siya, gagamitin lang natin yung ating Tafel equation. Tafel equation. H plus 2 electron minus. So it's controlled by activation polarization. Then this would mean that it will be N is equal to beta plus minus log I over I naught for each of zinc, and hydrogen. So in this problem, we need to compute for the rate of oxidation of zinc given the corresponding activation polarization data. V is equal to negative 0.763 volts. I naught is equal to 10 to the negative 7 amps per cm squared. Beta is equal to 0.09. For hydrogen, your potential or equilibrium potential is 0 volts. I naught is equal to 10 to the negative 10 amps per cm squared, and beta is negative 0.08. And we also compute for the value of the corrosion potential, VC, or yung intersection lang nila. So basically, we're just looking for the intersection of our two polarization curves. So credit to Ma'am Ayla for this graphic. So for the hydrogen reaction, yung hydrogen natin, this is our reduction half reaction. Since makita natin, your potential is higher. The equilibrium potential is higher. So this will act as our cathode. Meanwhile, our reduction reaction. Meanwhile, yung zinc natin, lower yung equilibrium potential natin. This is around negative 0.77. So pataas naman siya. This is your anodic reaction. Eraser. Eraser. So we have now equations for both hydrogen and zinc. So nanggaling lang yan sa overpotential, since we know that overpotential is equal to your voltage at overpotential minus the voltage at equilibrium. So linipat lang natin to the other side. We have this one. So eto magiging negative siya. Then we equate both equations to get your your corrosion potential. VC here and your IC here. So equating these two equations to get the intersection here, lines lang kasi siya, we get ito. So we now input our values for the equilibrium potentials, yung BH, BZN, and I naughts for each. We get, eto, wait, tama ba? Sorry. So ang ginawa ni Ma'am Ayla dito, in-equate niya. But anyways, same banana. Then we input our equations. So yan. So to get log IC, ang ginawa niya is in-isolate niya lang yung I. Kinombine niya yung equation to isolate I here. Then solving for the equation, he get that IC is equal to 10 to the negative 3.924. Ito siya. It's equal to 1.19 times 10 to the negative 4 amps per cm squared. So we now have IC. Then to get ano ba? To get V, we just input IC back into one of our equations. So babalik lang natin siya either dito or dito. And we can get our corrosion potential. Sorry. We have here. Rate of oxidation. Hindi pala. So corrosion potential, babalik lang natin si IC dito. We get ito. Then for the rate of oxidation, we just use IC over NF to get this one. May tanong ba kayo?
Sir, so kapag yung sa equation using over potential, yung equation is just like parang lagi lang siyang positive yung beta kasi nasa value ng beta yung sign ng positive or negative na slope.
Paano ba? Ano to? Dito sa example ni Callister, iba lang yung convention niya. Ginawa niya lang positive and negative. Pero basically dapat alam lang natin yung sense kung paano papunta yung beta natin. Pero nga, pwede natin i-treat yung beta as always like positive na lang. Kasi i-vary na lang natin yung signs depende kung bababa siya or tataas. If that makes sense. Well, it makes sense. So ang important skill lang natin dito is dapat marunong tayong mag-equate ng dalawang equations. Ng polarization curves for two half reactions. 11 na. Ito. May tanong pa ba kayo?
Sir, dun sa concentration polarization, wala bang potential corrosion like V-core?
Sorry, ulit.
Hindi ba natin kailangan ng V-core dun sa concentration polarization? Hindi ba siya important for that polarization?
For concentration polarization, meron din tayong V-core. Makakuha rin natin siya, actually. So, let's go to the next example, this one. For concentration polarization, usually ganyan siya, di ba? Pwede mo siya i-erase. Balik tayo. So, for concentration polarization, let's say ganyan, and ganito siya. So, makakuha lang natin yung V-core kung saan siya mag-intersect with this one. So usually tumatama naman yung V-core natin dito sa IL or dito sa path na to. So makuha rin natin yung overvoltage or yung polarization potential natin or polarization voltage natin kung saan mag-intersect yung isa and yung concentration. Yung anode and yung cathode mo. Okay ba, Mon? I mean, nakuha mo.
Sir, saan po galing yung line?
Kunyari lang meron kang anode. Kasi usually yung concentration polarization natin, yan yung reduction. So kunyari, may nagko-corrode na sa kanya. If gets pa.
Okay, get. Thank you, sir.
Ito pala. So, combined polarization. So we can also use the same principle in, let's say, combined polarization. So we have a metal here. Yung metal natin, mas mababa yung potential niya. Ito yung magko-corrode. So yung plot na to, it's a Tafel equation. Then yung sa reduction natin, let's say acidic environment, so we have H plus 2 plus plus 2 electron minus 2 H2 gas. Yung plot naman nito is combined na activation and concentration. Then to get again yung corrosion potential natin, corrosion potential and your corrosion current density, we just equate these two equations. So mangyari lang dyan, we have ito and ito equal mo. Then makakanap tayo ng value of I and value of V here. So yan, same lang naman siya. I-equate lang natin equate lang natin yung dalawang polarization curves to get the intersection, to get your corrosion potential and your corrosion current. So this is simple mechanically. I mean, simple lang siya to understand. Ang trouble lang dito is yung math. Medyo mahirap lang mag-equate nito. But the beauty of being engineers is that we are not limited by paper and pen methods and or we're not limited by, let's say, the calculator. Meron namang Wolfram Alpha and other solving software na pwede natin gamitin. So we can use that to solve our equations, actually. So one such example is, where's my Microsoft Mathematics? So if hindi kayo aware, okay. So hindi kayo aware, si Microsoft is meron siyang math solving software. So ang tawag sa kanya is Microsoft Mathematics. So you can just input, let's say, x equals 2 plus, okay, 2 plus x is equal to 5 raised to x. Then, kaya nyo na mag-solve nung ating equation. So yan, so pwede natin gamitin yan when we are solving problems like this one. So baka hindi lang kayo aware na meron tayong ganyang software. And ang maganda dito, maganda integration niya with like yung equations builder ng Microsoft. So pwede na, ang ginagawa ko lang dyan ko na tinatype yung equation. Kina-copy-paste ko lang yung equation pupunta rito para ma-solve yung problem. So tips and tricks. So yan. So the challenge now in the mixed potential theory is now when we have mixed electrode systems. So this is something that's not really part of your module. Hindi na namin siya nilagay. But I believe that it's really important in the pursuit of materials engineering or in materials engineering, since most of our systems in the field is not hindi lang isang reduction, isang oxidation nangyayari. Usually meron tayong coupled na effects na nangyayari. So one example here is the effect of an additional oxidizer. So let's take, for example, we have metal M. Oh God. We have a metal M. So the metal M is involved is in a industrial setting in which yung corrosion niya is not only governed or not only affected by acid. So usually pag acidic condition we have H+. It is also attacked by, let's say, ferric salts. So pag meron tayong attack ng ferric salts, yung equation natin Fe3 plus E minus to Fe2 plus. So in this case, we have two reduction reactions and one oxidation reaction. So ang nangyayari dito, we can think of it as if inaatake ng both hydrogen, meron tayong hydrogen attack and meron din tayong Fe3 plus attack in the surface of our metal. So Fe3 plus attacks this one and hydrogen plus attacks this one. So ang kumakain sa metal mo is not only H plus or the acid, but also the action of your ferric ion. So since dalawa yung oxidant natin, Fe3 plus and H plus, dalawa yung nag-a-attack sa metal mo, meron tayong dalawang, we have two oxidants, we have two reduction equations we have to consider. This one and this one. So from the mixed potential theory, to get the total corrosion rate of the metal, we have to consider the effect of both of these systems. So to get that, dapat nating i-add yung reaction rate nitong dalawa. So adding the polarization curves of these two, we get itong bagong polarization curve na to. So this is the polarization curve, for the combined action. Eraser. So we erase this one. So yung highlighted in red natin, this is the polarization now for the total reduction. So makita natin, mas mataas na yung current niya than these two. Kasi inad na nga natin siya. And to get the corrosion potential and the corrosion current for the metal, we basically look for the intersection of this metal with this total reduction curve here. So makita natin na ito na, or let's erase everything again. This one and this one, ito na yung magiging I core and E corrosion natin for metal M. And since logarithmic yung scale na to, log siya, makita natin that there will be a large increase in the corrosion rate due to these coupled effects. Yan. So, malaking increase niyan. Kahit mukha siyang maliit, malaki na yan. That is very big here. So yan. So to get the corrosion rate in a coupled system, we need to add the polarization curves of our oxidants and our reductants. Tama. And get the intersection of the total of those. So ito, this one. Clear ba to? Before I proceed to something a bit more difficult.
Sir, yes, sir.
Okay. So, wait lang. Water. So ito yung pinakamadali na mixed electrode system. Another way we can apply your mixed electrode system, or actually, usually yung polarization curves natin, ginagamit natin to in this one. This is now a galvanic couple. In this kind of galvanic couple, we connected a corroding metal, zinc, with an inert metal, platinum. So in this case, let's visualize it as parang ganito. Meron tayong zinc dito. Then meron kang platinum dito. Let's say this is at an acidic environment. So we have H plus ions here. So makita natin that for this kind of system, ito, your oxidation would happen only at zinc. Actually, wait. Ganun tanong yan. Bakit ang platinum hindi ma-a-attack ni hydrogen? Tanong ko pala muna yan. Bakit si platinum hindi siya mako-corrode ni hydrogen? Also, shout out sa mga lahat na pumasok today. Hello. Morning. Yes. Bakit si platinum hindi siya ma-attack ni hydrogen? Sa tingin nyo?
Sobrang baba ng potential ng platinum.
Sobrang baba ba?
Joke lang, mataas pala.
Mataas. Sobrang taas kasi ng potential, ng reduction potential ni platinum compared sa hydrogen. Kaya usually hindi yan nagko-corrode. Para lang siyang gold, mas matindi lang siya. So yan, yung gold nyo hindi yan matutunaw sa acid. So yun, so kaya si platinum, hindi siya ma-atake. So makita natin yung oxidation natin will be on zinc only. But since platinum is exposed in the environment, your oxidation will only happen at the zinc surface. Again, zinc to zinc 2 plus 2 electron minus. But since platinum and zinc are connected and it is in the environment, yung reduction potential ng hydrogen, reduction reaction ng hydrogen natin may occur at both the zinc and the platinum surfaces. Ang dami ambulansya ngayon. So, in both of the surfaces, we have the reduction reaction. 2H plus plus 2 electron minus 2H2. So it will happen at zinc. H plus will form 2H2. It will also happen at platinum. It will form hydrogen gas. So in the abstraction of the hydrogen ion to the H2 gas, magkakaroon tayo ng electron transfer to here. So you have electrons here, paalis, and paalis. So lalabas yung electron natin, tama? Makakain yung electron natin ni hydrogen ion. So since zinc and platinum are electrically connected, and si platinum, nagtatanggal din siya ng electron, yung electron na yan, kukunin niya mula kay zinc. Kinuha niya kay zinc yung electron, since si zinc, pwede siyang mag-give off ng electron by oxidation. So since platinum is connected to zinc, the connection of platinum to zinc excarbates or tawag doon, pinapalala niya yung corrosion at zinc. Since kumukuha rin siya ng electron from zinc para ma-fulfill yung reduction reaction ni hydrogen at its surface. So makita natin that for zinc, instead of being attacked by just one, by hydrogen at its zinc surface, it would also be attacked or it would also be affected by the reduction of hydrogen at the surface of the platinum, which in this case is actually very, very fast. Looking at here, and the coupling of platinum and zinc will result to very, very high corrosion in our zinc surface. So adding the reduction or adding the potential curves for the reduction of hydrogen at zinc and reduction of hydrogen at platinum, makakuha natin ang eraser. Parang kung tanga, hindi ako nag-zoom in. Zoom in? Yes. So we have, okay. Zoom in. Okay. Draw. So again, we have zinc and hydrogen. So meron tayo nung zinc and platinum. So meron tayo nung reduction at the zinc surface, H plus, H2. And we have the reduction at the platinum surface. So we add the rates of both polarizations. We get ito. This is now your total reduction rate. And we intersect that with your total oxidation rate. And since oxidation only happens at the zinc surface, dito lang siya. And we get their corrosion, your corrosion current. Corrosion happens at this point with current na ganito kalaki and potential na ganito kalaki. Clear ba siya? Clear all drawings. Pwede pala kayo mag-drawing dun sa screen. Okay. So, may tanong ba kayo regarding this? So, medyo simple lang siya. Similar lang siya dun sa previous example. Hi.
So, sir, hindi natin papansinin tong unang intersection.
Paano unang intersection? Ito. So, yung mga ibang intersection na yan, ito yung intersection in, let's say, pag hindi ka coupled with platinum. Hindi ka. Kunyari ito. Ito if zinc lang yung meron. Okay no, actually, yung gano'n siya. Ang gandang tanong yun, Cedric. So, okay. So, makita natin dito that, yun pala, isang other data na makuha sa polarization curve is kung ano yung extent in which we can see or kung gaano kalala yung mangyayari after we couple something to our anode. So makita natin from here, dito, if wala si platinum, walang platinum, yung corrosion natin would happen only here. Mababa lang yung corrosion current. But once we coupled natin with platinum, ito na siya. Dito nakalakas yung corrosion mo. So yun. Then, hindi, mamaya na. Later na iba. But for this case, yung total corrosion natin would be ito lang. Hindi na natin ito papansinin. Yun. May tanong pa kayo?
Sir, medyo dun sa part sa polarization, sir.
Oh.
Kasi 'di ba for non-equilibrium siya tapos yung nakuha mong values pag i-solve mo yung potential ng corrosion.
Sorry ulit?
Yung 'di ba yung intersection yung makuha mong value is potential ng corrosion.
Oo.
So paano po yun marirelate sa kinetics ng non-equilibrium? Kasi sabi dito sa module na parang saan ba yan? Teka lang.
Headphones.
Ayun, sabi we can calculate the corrosion rate if data are available from corrosion potential and polarization behavior. So, paano po makuha yung corrosion rate based sa plots ng polarization?
Yung intersection.
Oo nga po, di ba potential value po yun?
Sa corrosion rate natin, ang corrosion rate natin, R, is just equal to I over NF. Where I is yung current. So kaya natin nahanap yung current, ano tawag din? Yung corrosion current natin para makuha natin yung rate of corrosion rate. So
Okay.
yung sa potentials naman, basically kailangan lang natin yung potential since kailangan natin malaman kung saan siya maglalay in the y-axis. Yung I0, basically. So thank you. May tanong ba kayo? Okay, I take silence as no. Next, we go into clear all drawings. Clear all drawings. Bakit ayaw bumalik? Close. We go into this one. So this is the challenge. So what now if we have two corroding metals in a let's say an acidic solution, an acidic environment. So dito makita natin that both metals M and N would corrode since M and N would corrode since bakit nawawala yung pen ko? M and N would corrode since yung kanilang reduction potential is less than H2. Due to galvanic coupling, we'll see that the corrosion rate of the more noble metal N is decreased while the corrosion rate of the more active metal M is increased. So ito yung effect ni galvanic corrosion. Kaya yung galvanic corrosion is really, oh my God. It's really detrimental since sobrang laki ng corrosion increase dun sa less noble metal or dun sa corroding metal when kinouple natin siya with another metal. That's why we don't like galvanic corrosion. We don't like pairing dissimilar metals together. It's due to this polarization curve. So now let's look at this mixed electrode system. M and N are connected to each other. So it would look something like this. M and N are electrically connected. They are in an environment in which they are acidic. So similar to kanina, dun sa ating platinum and metal M, or platinum and some kind of metal, in this case, your hydrogen, H+, would react in both surfaces. Meron tayong reduction of hydrogen at metal M to form H2. And meron tayong reduction at metal N to form H2. Each having electrons and electrons. So for this one, you have H2. Sorry. H plus 2H plus 2 electron minus to form H2. So yun yung reduction potential mo. And meron tayo at metal N and at metal M. At the surface of N, at the surface of M. So nangyayari yung reduction reaction natin. So adding both of these together, we have this total reduction here. Total reduction natin is ito. Now, from the mixed potential theory, again, dapat total reduction and total oxidation. Now, let's look at the oxidation reactions. Metal M and metal M will both oxidize to this following. So, for M, we can signify as M to form Mn plus Ne minus. While for N, it's N M plus Me minus. So basically, nag-form tayo ng ions in the surfaces. And they would have the polarization curves na for M, this one, and for N, na ito. Then again, from mixed potential theory, we need to add these two. We get itong corrosion, itong oxidation curve na ito, or oxidation polarization, or the anodic polarization curve here. And to get the corrosion rate for our system, we just get the intersection of the two dashed lines. So, pupunta siya dito. So, yung corrosion ni M, corrosion involved in M plus N has speed of I. Itong intersection na I na to. So, that's one information that we get. But in galvanic corrosion, but this information, this tells us the corrosion rate for both of the metals. Since kinukuha na yung I, or, so notice here, capital I na siya, this is now current. So usually pag coupled yung systems natin, hindi natin ginagamit yung current density, we now consider yung current na mismo. Since pwedeng magkaiba yung surface area ng metals natin. So in this case, yung intersection na yan, that is yung corrosion for both metals M and N. In galvanic corrosion, it is more important for us to know the individual corrosion rates for, let's say, metal M and metal N. So now, how would we get that back? So dito na pumapasok yung ating corrosion potential, E corrosion. So let me zoom out. zoom out. And erase all ink. Erase all ink. And erase all annotations. Okay. So, na-establish natin from the intersection of the I of the total reduction and total oxidation. Sorry, nagsistall ako kasi kailangan kong yung pen. It's somewhere here. Ito yung intersection. And yung couple, yung E nung couple natin will be somewhere here as well. To get the corrosion rate for M and N, we just have to get the intersection. Yun. We get the intersection of pen. Bakit hindi ako pwedeng gamit ng pen pag nakaano? E couple. Yun, straight. I'm proud of that one. Ay, nawala. Hassle. To get the corrosion rate of M and N, what nawala? To get the corrosion rate of M and N in a couple, so corrosion rate of M and corrosion rate of N, corrosion rate of M on N and M, this would be yung E-couple natin. And kung saan tama yung E-couple natin or ano yung value netong potential na to with respect to the polarization curves of N and M. So makita natin here that yung sa couple, yung corrosion natin is almost equal to the corrosion at M. Meanwhile, yung sa N natin, yung corrosion mo is mababa lang. Dito lang siya. Clear ba to? Hopefully, hindi masyado. Clear ba siya? Nagets nyo ba yun?
Yes, sir.
Talaga? I'm doubtful.
Sir, so ang tawag dito, yung coupled na corrosion, yun yung parang individually na experience ng M tsaka N in combination of all the corrosion na nangyayari.
Sorry, ulit?
Yung dun sa intersection
Yung
nung
dash line?
yung dito.
Okay. Oh,
yung intersection na yun is parang yung na-experience ni M tsaka ni N individually pero considering all the factors for the corrosion. Or
yan yung total current in the system. So yung total current na yan, ang mangyayari dyan, mahati siya into two different currents experienced by N and M.
okay.
So dito, kasi masyado siyang maliit. So dito, ito yung annotate, text, draw. This one. So ito yung total. Ito yung M on N. Then yung sa clear. Then ito yung N on M. Siyempre tinuro ko para nakita niyo sa screen. Draw. Tapos ito yung N on M. Ito yung total. Clear all drawings. This is total. This is experienced by M. And this is experienced by N.
So parang sir yung dash line is just to calculate pero hindi siya yung
Okay, gets. Never mind. Sige, gets.
Total siya. So yung dash line natin, ang mas important na makuha natin dyan is actually yung corrosion potential. Since we can just put the corrosion potential on the on the equations of polarization for N and M, yung anodization nila or yung anodic polarization. Or in graphical terms, basically kung ano yung value ni E sa line na to and value ni E, value ni I sa dito. Clear ba? No. Clear ba ito? Okay. There's another thing to note here, is that if we look at the corrosion, if M and N are not coupled, hindi sila magkadikit, so M and N, no connection between them whatsoever. If hindi sila coupled, makita natin yung corrosion rate natin for N. Clear all drawings. For N, yung corrosion rate natin will be just the reduction. Okay. Close. Taas natin ito ng konti. For N, hirap. For N, yung corrosion rate natin is ito and ito. So dito siya. While for M, it's the intersection of the reduction at M, and yung oxidation ni M. So I corrosion ni N is ito, and I corrosion ni M is this one here. And makita natin, pag ginalvanic couple na natin siya, yung corrosion ni N bumaba. While yung corrosion ni M tumaas. So that's why we don't couple. We don't like to couple the similar metals because this would rapidly, or this would increase the corrosion rate of your less noble material. And since logarithmic scale na to, medyo maliit lang siya tignan. Pero once we translate this to a non-logarithmic scale, this actually will translate to about siguro mga spitballing about 2 times to 10 times faster corrosion rate. So in terms of time, let's say yung part mo is rated for 10 years, but we coupled it with a dissimilar metal that is more noble than it, then it will become just 1 year na lang yung lifetime niya, which is very detrimental, which we don't want to do. So yan, hopefully clear siya. Clear ba ito?
I-clarify ko lang po
Oh.
kung nagets ko. So, yung individual na total corrosion for M and N is the intersection ng total corrosion potential sa individual na anodic polarization curve.
Wait, what?
Sorry. So, di ba sir, meron tayong total na corrosion potential.
Yes.
Then to get the individual corrosion current, hanapin natin yung intersection ng potential with the anodic polarization curve to get the current.
Okay. So hinahanap natin yung value ni current at the for both anodization polarization curves at the potential E corrosion. Parang ganun yung sinasabi mo, di ba? Okay. So tama yun?
Okay. So yung total na gagamitin, yung total na corrosion potential na yung titignan. Yun lang
Yes.
titignan. Okay.
Yes. Kasi yun yung ginagamit natin since at that corrosion, at that system or at that time, or habang nagko-corrode siya, yung potential ng system mo is yun.
Okay, sir.
Kaya yun yung gagamitin natin for the system.
Thank you, sir.
Okay. So thank you for your wonderful questions. Beauty queen tayo ngayon. Clear all drawings. Ay, 11:37 na. So just permit me to go through the last topic. Ayoko nag-ano eh. Bagal tayo. And now, last topic, we have passivation. So this is a phenomenon observed during corrosion of certain metals or alloys. Alloys, di alloys. Gabi na kasi yan ang ginagawa ko mga alauna ng umaga kanina. This involves the loss of chemical reactivity under certain conditions. And passivation is a production of a thin passivation layer, usually oxide siya, that acts as a barrier for the reaction of the metal with the environment. So one common passivating metal is your aluminum, and one not common passivating metal is your iron. So depending on the environment a metal may experience, it may undergo either an active or a passive behavior. So what does that mean? So sa passivation curve mo, this passivation curve, this is just a polarization curve na mas malandi lang siyang tignan. So yung polarization curve natin, una activation polarization siya. Then pag tumaas yung potential mo, it may react with the environment to form an oxide film. And makita natin, bababa yung current here. And this indicates passivation. Then after a certain increase in the potential, it may go out of that and increase again yung ating corrosion, yung current. So meron tayong different zones. This is your active zone. Active for activation, polarization. You have your passive zone in which nagkaroon tayo ng passive character. So dito, your corrosion is stifled. Then after some increase pa in the potential, magbabalik tayo sa transpassive. So transpassive after passive, naging active na uli siya. So ang environment natin, this is just basically yung polarization curve, or basically kung paano na-set up yung polarization natin with the environment. So active yung behavior natin if mataas, if corrosion rate is high. So in this case, let's say condition 1. Sa condition 1, ito yung polarization curve mo. And intersects yung passivation curve natin dito. Here. This current is high. Ibig sabihin, active yung metal mo. Okay. Let's erase all ink. In number 2, passive siya. Pag passive naman siya, ibig sabihin, tumama si number 2 dito sa passive region. Here. So since yung intersection nito and ito is dito, and this is a lower current, so essentially protected yung bakal natin. Pag protected yung bakal mo, mababa yung corrosion mo, meron ka passive layer dito, and yan, mababa yung corrosion mo kasi mababa yung current density. Clear ba to? May tanong ba kayo dito?
Okay lang.
Okay. So, Sed, since wala ka namang tanong, paano pag ganito?
Passive muna siya, tapos magiging active.
Tingin nyo, paano pag ganyan? Paano pag yung cathode natin, or basically yung reduction natin tumama sa 3 points sa passivation curve mo?
Depende siya sa current?
It depends, but not... well, medyo tama na yun, siguro. It depends on the current. It's not as right, but it's getting there, siguro. Tingin nyo, paano pa ganyan?
Priority yung, mas mangyayari yung mas active.
Not really. Actually, nag-stall lang ako kasi kailangan ko uminom ng tubig. Pag-isipan niyo muna yan. So yan. So medyo tama si Meg na this actually depends on the current. So in this case, we have two stable states. Ito and ito. So your metal can either be active or passive. From the polarization curve alone, we can actually not make any conclusions. So yan. So dapat alam natin yung conditions in which your metal is exposed to. And we usually look at the metal. Depende kasi sa environment niya, pwede siya mag-shift from a passive state to an active state. So we usually don't want our metal to experience ito. Kasi wala tayong kasiguraduhan kung paano yung mangyayari sa kanya. And also, yung nasa gitna, this is a unstable state. Hindi yan natin kinoconsider. So again, pag nag-intersect siya, if nag-intersect siya in 2 points, here and here, both of these can be stable, but we need further information, i.e. we need to actually observe the system to draw any conclusions from this one. Clear ba siya? Oh my God, lamig. So digest niyo siya muna. So these two can be stable. This is not stable, can be stable, but we don't actually know whether passive siya or active in any point of time just from the polarization curve. We need to look at the system. Since nakita natin sa systems na ganyan yung behavior, it actually shifts from active to passive periodically depending on the environmental conditions. So yan. So may tanong pa ba kayo regarding this or other parts of the module? So dito na ako magtatapos for this one. So hopefully, hopefully okay naman or naiintindihan nyo naman yung kinetics of corrosion. Kasi nung ginagawa ko yung video nito, medyo ang haba pala nito. So di-discuss ko na lang siya. So may tanong ba kayo? Additional questions regarding this or other lectures in Module 2? Oh my God, so cold. So shout out na rin sa lahat ng participants natin. Hi guys. Thank you, thank you. Thank you. So subscribe to my Zoom channel. Wala ko ng overlays. Dun, 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 dun. So plug ko na rin ang aking YouTube channel kung saan nandun ang ating supplemental MatE videos and other stuff, siguro. And oh my God, it's so cold. Ayun. So if wala na kayong tanong, wala na kayong tanong? Wala na kayong tanong, no? So thank you for joining me today. So this has been a very long session, the longest I've been. Oh my God, and it's so draining. So ayun. So thank you everyone. And I'll stop my sharing and my recording.